Now that we've talked about the limits of functions and the fact that the limit of a function tells us where our function is heading, another key question that we want to talk about is whether or not a function is continuous. So first of all, if we think about the word continuous, meaning that we have no breaks in the function. Okay, so something that's continuous has no breaks. And if it's a function, remember that it passes the vertical line test. So if a continuous function is made up of those two words, then what we have is a function that has values for all x's in its domain. Okay, and that all of those values are connected. So we like to say that you can draw a continuous function without picking up your pencil. So that sounds real mathematical, but that's really all it is can I draw the function without picking up my pencil so that there are no holes and no asymptotes to jump over. So let's think about something in order for something to be continuous. There has to be a function value at every point, and there has to be no jumps or breaks, and the limit helps us with that because remember the limit said you approach the same thing from the left that you approach from the right. So we might have approached a hole, but we approached from the left and we approached from the right, and now we're going to say there's a point there, and that's going to fill that hole if in fact there was one. So in order for a function to be continuous, for every c in the domain, so for every number we pick, there has to be a limit, and that limit has to be equal to the function value. So now this might have had a limit as we approach from the left and the right, but there was no function value. So now when I approach from the left and I approach from the right, I have to approach that point. Over here, that point could have been down there. So that does have a function value at that point, but it is not equal to the limit. So in order for a function to be continuous, and this is important, this is called the continuity test. To test if a function is continuous, the limit from the left has to equal the, and I just said that backwards, so what I have coming up on the screen is the limit from the right has to equal the limit from the left, which means you have a limit and it equals the function. So the limit from the right equals limit from the left equals the function. And if all of that jives, then we have ourselves a continuous function. It really is just the idea that then we can draw it without picking up our pencil. So on our first two slides, I know that it looks pretty simple, continuous, because it looks it. But let's make sure that we can do the test. So if I ask you, is the function on the left continuous from A to B? So I'm only asking, is it continuous from A to B? Then first of all, no matter what I pick in between, any value, and so all those values we refer to as C, that every C value has a limit. So if you pick any point here and you say as x approaches that C right there, as I approach from the left and I approach from the right, I'm approaching the same point. So it does have a limit, and there is a point f of c. There is actually a point there, and the limit equals f of c. So that's what you technically have to go through mathematically in order to say that there is a continuous function. I think it's pretty clear that over here we have lots of points of discontinuity, and so we have a function that is discontinuous. We've got an issue here as well as an issue here. Here the limit from the left does not equal the limit from the right, so that right there says it's not continuous. Here the limit from the left does equal the limit from the right, but that does not equal the function value. Now, there are different ways we can talk about continuity. We can first talk about continuity of a function. If we are asking, is the function continuous, we are asking, is it continuous for its domain? Because each function has its own domain. For example, y equals x plus 2 is a line. Its domain is all reals. So if I ask you, is this a continuous function, I want to know that for every single x on the number line, is this function continuous? But if I ask you about y equals 1 over x, that is a function whose domain is such that x cannot equal 0. So if I ask you, is this a continuous function? Okay, notice I'm saying continuous function. I'm not just saying, is it continuous? Then you would look everywhere except at 0. So as long as to the left of 0 is continuous and to the right of 0 is continuous, then you say it's a continuous function, because you almost have to imagine that you can just pull out that x equals 0 piece, because that's not part of its domain. Now, I can also ask you, is it continuous over a piece or subset of its domain? And that's what we kind of just looked like. I might say, is it continuous from A to B? And if so, then it has to be continuous right up to the endpoint. Okay, so this is continuous from A to B. This is not continuous from A to B, because at A, the limit as we approach from the right does not equal that function value. We don't have to worry about approaching from the left because it has an endpoint, but the function value would have to equal the limit from the right. Okay. Now, we can also talk about point continuity. And point continuity can either be on the inside or on the endpoint. And whichever the case, if it's in the inside, so if it's between A and B somewhere, then you have to look at the limit from the left equals the limit from the right equals the function value. If you're only looking at an endpoint, like the pictures I drew here, you only have to look at it as it comes from the appropriate direction. So in this example here, we would want the limit as x approaches A from the right to equal whatever we get when we plug in f of A, and in fact it does not. But over here, the limit as x approaches B, we would want that to be from the left, and that would have to equal f of B, and it does, because as I approach from the left, I approach that point there. So the B one has a limit, whereas the one that's approaching A does not. So if it's on the end point, it only has to be from one direction. So just kind of a summary. What would cause discontinuity or a point of discontinuity? Remember that's when the left-hand approach and the right-hand approach aren't equal, or if there's not a function value. So I kind of just talked about that, but you got to approach from the same place from both directions, and it also has to match the function value. So when you're asked to test for continuity, first make sure that the function is there. Make sure that there's not a hole. And if there is a function value there, make sure that it's the same as the limit as you approach that area. And so they both would have to be equal. Okay. Now, if you are asked for continuity on a closed interval, remember interval notation, this means that the endpoints are included in the question. So the endpoints would have to, your approach from the left would have to equal the function value there. However, if it's an open interval, then that means the endpoints are not to be considered. So you're saying, is it continuous everywhere in between those 2 points, but not on those actual points? If you're asked, is it continuous from the right at a value, remember we said that if you're only approaching from one side, that approach, so the limit as x approaches a from the right, must equal f of a. And likewise, number 3, if I approach from the left, the limit as I approach from the left, the limit as x approaches b from the left must equal f of b. So you can have a one-sided continuity test or a full continuity test. Let's take a look at this graph, and let's talk about the continuity at these different points. So maybe even consider pausing this and you decide whether it's continuous or not at each of these areas. And be prepared to say why. Okay, so at x equals 0, so as x approaches 0, which is here at a, that is at an endpoint, so we only have to do a one-direction test. As I approach from the left to x equals 0, am I approaching the function value? And the answer is yes, this is continuous, or that is a point of continuity. At x equals 1, I have to approach from the left and the right, and I am not approaching the same number, so this is a point of discontinuity. X equals 2, and that's here, as I approach from the left and I approach from the right, I am approaching that function value, and so that would be a point of continuity. Now if I had meant for 2 to be lined up over here, then that would be a point of discontinuity. So if I was coming from the left, I was coming from the right, I'm approaching that oval, but that's not the function value, this is, and so therefore, depending on if I really meant that to be over there, we would say that is a point of discontinuity. So if we're talking about right above 2, that is continuous, but if I meant to talk about this mess here, that with the open circle, that would be a point of discontinuity. At x equals 3, we finally have something nice and clean. Go from the left, go from the right, equals the function value. That is a point of continuity. X equals 4 is at an endpoint. As I approach from the left, I hit my endpoint. I don't have to worry about approaching from the right. That is a point of continuity. Over the interval from 1 to 2, what's critical here is that 1 and 2, let's put that mess in the 2 there. 1 and 2 are in brackets, which means they're included. And we had points of discontinuity on the end, so this would not be continuous. But if I did this, where 1 and 2 were not included, now we are continuous because everything in between is continuous. So let's talk about some equations and how to look at, is it a continuous function and is it continuous over all reals? We've looked at this graph for 1 over x before, and hopefully you're able to sketch some of these basic graphs without a calculator. But you certainly do have your calculator to help you if you need it. Alright, so we got two questions. Is it a continuous function? And is it continuous over all reals? Those are two different questions in some cases, same question in other. In this case, our domain is x cannot be 0. It's all reals except x is 0. So we have to ignore this area right here because that's not part of our domain. So our graph is totally continuous everywhere else. So this one is continuous. It is a continuous function because if we take 0 out of it, because that's not part of our domain, then everything is continuous. But it is not continuous over all reals, because all reals is the whole number line, and we cannot start at one end of the number line and go to the other without drawing it. Without picking up our pencil. Next one, f of x equals absolute value of x. That graph, if you remember, looks like a V. All right. And so, is it continuous function? Yeah, because every approach from the left and the right equals the function value. Is it continuous over all reals? Yes, there's no break in that graph at all. So that is continuous for both. Next one, this is the integer function. The integer function, f of x equals greatest integer function of x. It's a step function. It's kind of weird looking. It goes something like this. Okay. And so that's a step function. And so this is not continuous over its domain because the domain here is all x's. You can do the greatest integer function of all x's. So this is a discontinuous function, and therefore it's also discontinuous over all reals. So I encourage you now to take your calculators and see what you can do to tell me whether these three graphs are continuous or not, both over the domain and or for its domain and over all reals. I would make sure that you remember that x to the 1/3 is the same as the cubed root of x. So take a second, take a look at what these graphs look like. Just decide if they're continuous, and then we'll come back with the answers. Okay, so hopefully you've tried the first one. The first one has a graph that is an exponential graph. It never crosses the x-axis. However, it does have a function value for every value of x. You can take 2 to any power. So this is a function that is continuous, and it is also continuous over all reals. Alright, take a look at the next one. This is a log function. Hopefully you remember that logs and inverses, logs and exponentials are inverses of each other. And by the way, if you're not sure how to use your graphic calculator, there are some tips and tutorials on the Blackboard page for how to use your graphing calculator. I encourage you to go to those tutorials. Alright, the log function is a function that goes kind of like this. So as you can see on this one, that for the actual function, it is continuous. There are no breaks in that graph. But if you ask over all reals, it is not continuous over all reals because there is no function value down here and the negative x's. And now take a look at your last one. So take a look at what that graph looks like, and you can put it in your calculator as x to the 1/3 power. Make sure you put 1/3 in parentheses, or you can put it in your calculator as the cubed root of x. And so that graph looks kind of like a funny S, because you can take the cubed root of a negative, just not a square root. And so this one is continuous across the board. So looking at graphs help a lot, but thinking about what your functions issues might be to cause points of discontinuity helps a lot as well. Now, remember those rules of limits that you could combine? The same idea is you can do that with continuity. If we know that x to the 14th is continuous, and we know 20x to the 4th is continuous, then adding them together will keep them continuous. So anything where you add or subtract or multiply pieces of continuous functions together, those will keep continuity. However, remember that things like denominators cause problems, so you have to look at them. In the next one, 5x, if you just graphed 5x, that's continuous because that's a line. 2 minus x is continuous. And if you think about x squared plus 1, anything you put in for x is going to get squared, which makes it positive, which means we'll never have a 0 in this denominator, which means this will never cause problems. And since that will never cause problems, it's continuous. All the pieces are continuous, so this is continuous. On the h function, x plus 3 is continuous because it's a line. X squared minus 3x minus 10, if you graph just that piece, it is a parabola, and a parabola is continuous. However, we have put that parabola in the denominator. So if that were up top, then we'd be fine. So both of these are continuous, but because we created a denominator, we have to look at that. And so we have to say that x squared minus 3x minus 10 cannot be 0. So it's a continuous function except for the fact that we put it in the bottom. And so if you factor that, you get x minus 5 and x plus 2. And so x cannot equal 5, x cannot equal negative 2. So this function is continuous except at x equals 5, x equal to 5 and x equal to negative 2. And if you don't believe me, take a look at the graph. Okay, so we took two things that were continuous, we put them together, and that was fine, except we created a denominator which caused trouble, and it causes trouble at 5 and negative 2, which means we have points or areas of discontinuity. Now we're just talking about basic continuity here. There are different types. Removable continuity, that's your hole. There are ones called jump discontinuity, that's kind of like the stair step thing that I showed you, where it's consistently jumping. Osculating discontinuity is where you have something that has to do with positive and negative. So it might be a positive value over here, but then you have a negative value here. And actually, let me think here. There's a better graph for osculating. Osculating is when if you plug in one value for x, you're going to get a value up like a positive value, but then when you plug in another value for x, it jumps over to the negative, and so it keeps going back and forth. Okay. And there is something called infinite discontinuity, which we don't see much at this level in calculus, but we look at that at higher ends when it's important. Okay, so remember I said there were two questions, and we've actually answered one of them, and that is how to determine where a function's going. And we can determine that by looking at its limit, its function values, and its continuity. And once we do that and we have an idea of where it's going, the next discussion is going to be how fast is it getting there. So we've answered the question, where is it going? The three things that tell us where it's going are the limits, the function values, and the continuity. And then next, as I said, we're going to talk about how fast it's going to get there. So this wraps up what the material for A2, which was on limits and continuity.